Hi everyone, here's today's question. I fitted a regression where y, the dependent variable, was skewed, but the residuals came out normal. How can this be? Isn't it an assumption that the y must be normally distributed for the residuals to be normal too? Okay, so before I show you an example, let's address these. The first one is yes, it can be. The second one is actually it's not an assumption that y must be normally distributed for the residuals to be normal. The actual assumption is about the error term, let's denote it by this, is the assumption is that it's normally distributed. The error term is normally distributed because we can't see the error term. The stand-in is like the residual, so we test that the residual, hence the error term is normally distributed. But even if the error term is normally distributed, it does not imply that y is normally distributed. Okay, that's the first bit of the question. So it does not imply that. What it does imply is that y, given any x, your IV, is normal. So there's a distinction between saying that the dependent variable is normal and y given some x is normal. So this is like saying that a conditional distribution of the dependent variable given the x's is normal. Now if that sounds like gobbledygook, let's look at an example and it should be clearer. So I'm just looking at a simple example, bivariate regression. I've got just one covariate. So that's my dependent variable. It's a scatter plot of y against x. X can take values from 10 to 50 or by observations that x is 10, 30 and 50. So you can imagine that if I regress y on x, I'm going to get a line going through all the way up there. Now let's look at the QQ, normal QQ plot for y. This is like a plot that can help us to tell us whether the thing is normal. So if it were normal, these observations for the y should lie pretty much on this line, but you can see it's way off this line, suggesting y is not normal. The histogram, the associated histogram looks like this. You can see that it is not a bell-shaped curve, but remember for checking the distributions, the histogram is not, we shouldn't use this because these shape will depend on the widths of these things, which is a bit subjective. So for that reason, guys, we always look at it better to use a normal QQ plot over the histogram. Okay, so we can see that y isn't normal. We can even test it. So I've got the skewness measure here. It's positive, so it's y is positively skewed. And the Shapiro-Wilk normality test, the null hypothesis is that it's not it's normally distributed, and the p-value is very tiny, times 10 to the minus 11, basically around 0. So we reject, very strong evidence to reject the null, pointing to that it's not normal. Now let's regress y on the x. Right, so here's my third picture. I regress y on the x, and in the left column are the plots for y, my dependent variable, showing you, this is produced from earlier, just showing you that's not normal. Now look on the right column, look at the normal QQ plot of the residuals from regressing y on x. It's pretty much on the line, and we can run a Shapiro-Wilk test on the residuals as well to test whether it's normal. Yep, so running on the residuals, the null hypothesis is that the errors are normally distributed. The p-value is 0.08, bigger than 0.05, so evidence not to reject the null of normality of the errors. Well, that is the assumption of classical assumption of regression, or should I say assumption of classical regression. Right, so what I've shown is the first demonstrated that your y might not be normal, it might be skewed, yet your residuals from running a regression could come out normal. In other words, if you find that your dependent variable is not normal from a QQ plot, say, it doesn't mean you got to run out and do a log transform or do some other kind of transform straight away. You can run it first, y on the x's, and then look at your residuals first. Okay, next I want to look at the second bit, because the assumption hasn't been memorized or written stated correctly here. We now know it's not that y is normally distributed. The fact that the error term is normally distributed implies that the conditional distribution of y given x is normal. So let's look more what this is saying. Okay, so the top left is a scatter plot of y versus x reproduced with now the regression line running through it. What it means to say y given x is normally distributed is, say, when x is 10, we take all these observations corresponding to the y, you can see running between 20 and around 60. We take all those observations and do a QQ plot of them. We'll get this. Okay, so all those lines, dots are these dots. And you can see they lie about on that line, suggesting they're normally distributed. We can do the same for the other x fixed at 30. So what's the distribution of y given x? X at 30 here. It's here. And you can see it's also around the line. Finally, what's the conditional distribution of y given that x is 50? It's here. If we run a Shapiro-Wilks test on all these three, we can show that they are all normally distributed. So what we've seen is that while y itself is not normal, the conditional distributions are all normal, and that is the assumption that we need for regression. Okay, so today we've looked at an example of this and we've corrected this. Remember the assumption that the conditional distribution of y given x is important for the inference. So when you're doing hypothesis tests, when you're computing confidence intervals, it has no bearing on the coefficient estimates you get from regression. And also, if your distribution, your conditional distribution of y given x is not exactly normal, is just slightly off, slightly skewed, then you're probably fine if your sample size is quite big. So by all means run transformations on your y if your errors comes out not to be normal, but don't think you need to transform y right at the beginning because you see that it's skewed. Okay, good luck with your modeling.